Hi guys, welcome back to the channel. So when it comes to cost, Lambda charges you based on the amount of memory that you allocate to the function and how long this function runs for by the millisecond. And it also charges you a fixed fee of 20 cents per million invocations. There can be other costs involved, such as the data transfer cost, but also when you enable certain features like allocating additional storage space to the temp storage, or when you use provision concurrency. But for the vanilla on-demand functions, you are paying for those two things: how long your function runs for and how many invocations you get. Now, the cost per millisecond of execution time is scaled proportionally to the amount of memory that you allocate. So 1 second of execution for 512 meg function will be 4 times the cost for 1 second of execution for 128 meg function. And the most effective way to reduce your Lambda cost is to make sure that you don't allocate more memory than your function actually needs. Before we talk about how to right-size the memory setting for your Lambda functions, it's also worth pointing out that for the vast majority of your Lambda functions, there is likely no meaningful cost savings to be had. And the Lambda cost itself is usually pretty far down the list of the most expensive items in your monthly AWS bill. There are exceptions to this, of course. As the famous saying goes, we should forget about small efficiencies. Say about 97% of the time, premature optimization is the root of all evil. Yet, we should not pass up our opportunities in that critical 3%. So the trick is in identifying that critical 3% of cases where we should optimize our Lambda function for cost savings. For that, you should always optimize the memory setting for functions that use provision concurrency, because provision concurrency has an uptime cost per month per unit of concurrency, and that cost scales proportionally to the amount of memory allocated to the function. For example, one provision concurrency for 128 meg function has an uptime cost of just $1.40 per month, plus variable costs based on the number of invocations and execution time, as we discussed earlier. But one provision concurrency for a 10 gigabyte function would have an uptime cost of $111.61 per month, plus those variable costs as well. With scaling effects like this, it's easy to make mistakes that can increase your Lambda cost by orders of magnitude. And another group of functions that fall into that critical 3% are functions that are invoked often, perhaps millions of times a month, and have a long execution time. So we can likely make meaningful savings on them by allocating less memory. And this usually works great for functions that spend a lot of its execution time just sitting idle and waiting for a response from an API call to some other service. So all their CPU cycle are just getting wasted anyway. And funny enough, in some other cases, it might be cheaper to allocate more memory, not less, because the amount of CPU resources and the network bandwidth is allocated proportionally to the amount of allocated memory. So more memory equals more CPU cycles equals getting whatever CPU intensive task done faster. And since we are charged by the millisecond, so faster execution at a higher cost per millisecond can sometimes work out to be cheaper than a longer execution time at a lower cost per millisecond. Luckily for us, we don't have to rely on guesswork. We can work this out using a data-driven approach. Before we get into that though, let me just steal your attention for a second here. Hi, let me tell you about my upcoming workshop, Production Ready Serverless. If you want to step up your serverless game and really become a better developer with skills that are highly sought after in the market, then this is one for you. Most workshops only teach you the basics, and they don't cover the practices that are so important in the real world, such as how do you test your application, what are the security best practices, how do you handle errors and monitor and debug your application. All these are skills that are crucial in running applications in the real world. And I've been running serverless in production since 2016. And I've learned a lot about what it takes to actually build a production-ready serverless application. And in this workshop, I'm going to teach you everything I know. Go to productionreadyserverless.com and get up to 30% off
by signing up early using our early bird tickets. Now, back to the video.
Alex Calzaboni, who now works at AWS, created a tool called the AWS Lambda Power Tuning, which is a step function state machine that can invoke a target function against an array of different memory settings and capture the performance and cost and help you find the best memory setting for your function based on performance, cost, or a combination of the two. First, you do have to install the state machine, and I find it easiest to install this through the Serverless application repository. A link to the app is available in the description. And once it's deployed, you can start an execution using a JSON payload like this, which targets a Lambda function with an array of memory settings to test and a payload to invoke the function with. And with the balanced strategy, I'm asking for a recommendation that gives me the best bang for my buck. And once the state machine finishes, you can check its output tab and find the best memory setting, which is 256 meg in this case, and a URL where I can see a visualization of how the performance and cost of this function changes with each memory setting. In this case, it shows that we received a significant performance boost when we increased the memory allocation from 128 meg to 256 meg. But adding more memory beyond that gave us diminishing returns, but the cost per invocation went up significantly anyway. That's why the state machine recommends that we use 256 meg for our function. This is a really powerful tool to have in your locker, and when it's used in the right circumstances, it can give you significant cost savings. But once again, you shouldn't do this by default because there are no meaningful cost savings to be had in most Lambda functions. And this cost saving is not free. You still have to work for it, including but not limited to having to capture and maintain a suitable payload to invoke a function with, and to plan and execute those state machines for every function. And then there's also the cost associated with running the state machine itself. And you still have to repeat this process every time a function is changed. And you have to update the invocation payload and rerun the tests. And finally, and the most significant cost of them all, is the time that you have to put into doing all of the above. If you're using Lumigo, then a good way to identify targets for power tuning is to go to the Functions tab and then sort your functions by cost in descending order. Here you can find functions that have a meaningful cost and are allocated with more memory than it's actually using, which you can see in the average memories column. These are the functions you should consider power tuning. And as I mentioned earlier, you should also optimize functions that are using provision concurrency, because the uptime cost for these functions can be significant, and using the wrong memory setting here can have a huge impact cost-wise. Another way to cut down on Lambda cost is to switch to the ARM-based Graviton 2 processor, which is about 25% cheaper per millisecond of execution time compared to functions that are running on x86 architecture. But before you do, please test your workload on both the x86 and ARM architecture. The launch blog post from AWS mentioned a 19% better performance in the workloads that they tested, but reports from the community has wildly different results. And in some cases, I've seen ARM-based functions run over 60% longer than x86-based functions. So depends on your actual workload, you may have a very different result. Having said that, if your function is I/O heavy and spends most of its time just waiting for responses from other AWS services like DynamoDB, then they're usually good candidates to switch to ARM because the CPU performance is not going to have a big impact on overall performance in these cases. Finally, another way to save on Lambda cost counterintuitively is to use provision concurrency. Because you see, with provision concurrency, the cost per millisecond of execution time is over 70% cheaper. So if you're able to keep those provision concurrency busy, say 60% of the time, then you break even against the on-demand pricing, even though you are paying an uptime cost, and anything beyond that 60% would be cost savings. This technique would only work for high throughput functions, and there's a potentially steep penalty if you get it wrong because of the uptime cost. And there are operational overheads for using provision concurrency as well. So as far as optimizing Lambda cost is concerned, it's not a technique that I would recommend unless you really know what you're doing. Instead, you should use provision concurrency as a way to eliminate Lambda cold starts. Let me know in the comments if you want me to do another video on the provision concurrency and when you should use it. I'll see you guys in the next one.